Hello, thanks for coming to my talk. This talk is entitled Solutions to Stable SDEs. It is joint work with my supervisor Leif Dering of the University of Mannheim. I've started with this reference slide so that if you want to find it at the end, it's easy to locate it. Just included these three references because these three papers will I'll mention theorems that are included in those papers later in the talk. So here's the structure. I'm going to start by talking about the specific problem that we approached, then briefly look at some existing work, partly just because it's interesting, but also because it directly inspired the approach that we took, and then look at the extensions that we've managed to develop from that existing work. So first, the problem. We're interested in weak solutions to driftless stable SDEs. So just to remind you what that is, it's a triple of X, a stable process on the real line, which is associated with some particular probability space that I've denoted by curly P, and Z, another stochastic process on the same probability space, which we call the solution process, and which satisfies this integral equation, usually written in a sort of shorthand, but here written out in the full form. So this little z is the issuing point of this solution process on the real line, and sigma is a non-negative Borel measurable function. This is then moving over the path of the, integrating over the path of the stable process. One example of a weak solution is a trivial solution. So if sigma is equal to 0 at the issuing point z, then one possible solution to this integral equation is that z doesn't move at all, it just stays at the issuing point for the entire time. So it's one possibility, but there are far more interesting possibilities, and we'll use the term non-trivial to describe any weak solution for which the solution process is not just this constant process. So our problem is that not every choice of sigma allows for a solution, well, solution process Z as solution X, Z, and P, and some choices of sigma allow for multiple solutions, and it's possible to describe conditions on sigma that correspond to existence or perhaps uniqueness of solutions. So now let's take a look at some existing work for a particular class of stable processes. Work on this problem was started by Engelbert and Schmidt. Well, at least this is the sort of earliest famous approach. With Engelbert and Schmidt in 1981, they considered just the Brownian motion, which is a stable process with alpha equal to 2, the only stable process with continuous paths, and they showed that these two conditions are equivalent. The first is that for every possible issuing point in the real line, there's a non-trivial weak solution to the Brownian SDE. That's equivalent to sigma to the minus 2 being integrable over all compact sets of the real line. 16 years later, Zanzotto managed to prove an extremely similar theorem, but now for a wider class of stable processes. So Zanzotto proved this for alpha stable Levy processes on the real line with alpha in 1, 2, not including 1, including 2. So 2, like I mentioned, is the case of the Brownian motion. That's of course the theorem of Engelbert and Schmidt, but for alpha less than 2, these processes can now have discontinuous paths. They're still Levy processes, they still satisfy the scaling property of Brownian motion, although now with a different scaling factor, that's exactly alpha. So otherwise they're different processes, but still in this class of stable processes. So Zanzotto showed the equivalence of the following two conditions. First, existence of a non-trivial weak solution to the stable SDE for every issuing point. And second, integrability of sigma to the minus alpha for all compact subsets of R. So that exactly includes the result of Engelbert and Schmidt, because in Engelbert and Schmidt's case, this alpha is equal to 2. So this success by Zanzotto of extending Engelbert and Schmidt's theorem to just almost directly to a broader class of alpha made us think that the same or similar might be possible for other scaling factors alpha. So in general, stable processes can have alpha between 0 and 2, not inclusive of 0, inclusive of 2. But as you get closer to 0, the behavior of the process becomes, in a sense, more volatile and less similar to the Brownian motion. But so we had kind of an idea that an extension further might be possible. One problem with that is that both Zanzotto's theorem and Engelbert and Schmidt's relies heavily on the local times of the process, which is this function L in two variables, time and space, satisfies this integral equation. The local time is a key element of the proof of both Zanzotto and Engelbert and Schmidt, but it doesn't exist for alpha stable processes with alpha less than or equal 1. So it's not available to use as a tool for studying SDs in that case. So we had to work around that. But before we start looking at that, it's worth looking at another theorem of Zanzotto's. So this one here, this first one from 1997, was about existence of a non-trivial weak solution, but those solutions need not be, there's no uniqueness involved here in this statement. So certainly the trivial solution may also exist, and Zanzotto's not saying anything about that. In 2002, he managed to prove this sort of companion theorem to that first, which is that there exists a unique weak solution, this time not saying anything about non-triviality, to this SDE equation, if and only if every point of the real line satisfies exactly one of these two conditions. Either sigma to the minus alpha is integrable on a ball around that point, or sigma is 0 at that point. The sigma is 0 corresponds to existence of the trivial solution, and integrability around the ball corresponds to existence of a non-trivial solution. And the fact that every z satisfies exactly one of these is what ensures that the solution is unique. So you can't have one or the other existing from when issued from the same point. So now we can take a look at the work that we did extending this from Zanzotto to transient stable processes, which is alpha less than 1. And those astute of you might have noticed that it doesn't include the strange middle case of alpha equal to 1. I'll try and talk a bit about that at the end. So before stating the theorems, a definition needs to be given. This is for X and alpha stable Levy process on R. A Borel set is called thin at some fixed point Z in R if, when the process is started from that point Z, the set B is hit at positive time almost surely. So that point Z is not regular for the set B. Because X is a strong Markov process, Blumenthal's 0-1 law applies here, and this probability of hitting at time 0 or not is also 0-1 law. If alpha is greater than 1, then any thin set for the stable process at some point satisfies this inclusion. So B is a subset of R subtract some ball around the point. So now we can take a look at the two theorems that we proved that are companions to those of Zanzotto and of Engelbert and Schmidt. The first is this: for alpha now less than 1, the following are equivalent. For every issuing point in the real line, there exists a non-trivial weak solution to the stable SDE. If and only if, for every point of the real line, there exists a set B which is thin at that point, such that sigma to the minus alpha is integrable against y to the alpha minus 1 on the complement of this thin set. So, as mentioned just in the previous slide, for alpha greater than 1, complements of thin sets, well, that's essentially just a ball around the point. But for alpha less than 1, that can be more complex. A thin set can get arbitrarily close to a point and still be thin, as long as it's somehow small enough, which is of course defined in a rigorous way. So that the thin set is essential in here. We can't substitute that with some ball around the point and get an equivalent theorem. The integral condition is of course reminiscent of that of Zanzotto and Engelbert and Schmidt, but it has this extra polynomial factor in there, which, since alpha is less than 1, will make the integral test harder to satisfy by sigma. Some are more restrictive on sigma. The second theorem that we have is companion to Zanzotto's second theorem from 2002, which is that these two conditions are equivalent, the first being that there exists a unique solution to the SD equation for every issuing point z, and the second being that for every issuing point z, exactly one of the following two conditions holds. And this, of course, this one or the other is for exactly the same reason as it is in Zanzotto's. First, there exists a set B which is thin at z for the process x, such that this integral condition is satisfied. Sigma to the minus alpha is integrable against y to the alpha minus 1 on the complement of B, or sigma is 0 at z. Once again, that second condition corresponds to the trivial solution existing, the first to a non-trivial solution existing, and the fact that z satisfies exactly 1 means that the solution is unique in law when issued from every point. Thanks very much for watching. I'd be very happy to answer any questions you have.